Hi guys, welcome back. Today we'll be looking at another room on networking concepts. First, you go to search, and from there we type networking. I already know the room, but just to show you how to search free rooms, networking. Then we are going to what? Oh, there's no T there. Networking. Subscription type is free. So this is the room we're interested in, networking concepts. I've started this room before, so yeah, I'm going to reset my progress. Yes, reset my progress. And this is a room that we are going to learn about the ISO OSI model and the TCP/IP protocol suite. Introduction. Have you ever wondered why you need an IP address to access the internet? Is it true that an IP address can uniquely identify the user? Are you curious to learn what the life of a packet looks like? If the answer is yes, let's dive in. This room is the first room in a series of 4 rooms dedicated to introducing the user to vital networking concepts and the most common networking protocols. This is the free room, and this is what we are going to be looking at. This room expects that you know terms such as IP address and TCP port number. However, we don't expect that the reader is able to explain such terms in proper technical depth. If you are unfamiliar with these terms, please consider joining the pre-security part. And by the time you are done with this room, you would have learned the following: the ISO OSI network model, IP addresses, subnets and routing, TCP, UDP and port numbers, how to connect to an open TCP port from the command line. Get your notepad ready, let's begin. Yeah, the OSI model. Before we start, we should note that the OSI model might initially seem complicated. Don't worry if you encounter cryptic acronyms, as we provide examples of the OSI model layers. We assure you that by the time you finish this module, this task will feel like a piece of cake. The OSI, Open Systems Interconnection Model, is a conceptual model developed by the International Organization for Standardization that describes how communications should occur in a computer network. In other words, the OSI model defines a framework for computer network communications. Although this model is theoretical, it is vital to learn and understand as it helps grasp networking concepts on a deeper level. The OSI model is composed of 7 layers: the physical layer, the data link layer, the network layer, transport layer, session layer, presentation layer, and the application layer. The numbering starts with the physical layer being number 1, while the top layer, which is the application layer, is layer 7. To help you remember these layers from bottom to top, you can use a mnemonic such as "Please do not throw spinach pizza away." You can also check the internet for other easy to remember acronyms if this helps you memorize them. Remembering the OSI model layers with their layer numbers is important, otherwise you are going to struggle to understand terms such as layer 3 switch or layer 7 firewall. Now, layer 1, which is the physical layer. The physical layer is also referred to as layer 1, and it deals with the physical connection between devices. This includes the medium, such as a wire, and the definition of the binary digits 0 and 1. Data transmission can be via electrical, optical, or wireless signal. Consequently, we need data cables or antennas depending on our physical medium. In addition to Ethernet cable shown in the illustration below and the optical fiber cable, examples of the physical layer medium include the Wi-Fi radio bands, the 2.4 GHz band, the 5 GHz band, and the 6 GHz band. If you are very curious, you can just come here and type Wi-Fi radio bands, Wi-Fi radio bands. Let's see images of that. images. Okay, I think it's just like an abstract thing, right? Okay, yeah, okay, we have a Wi-Fi router, and okay, just talking about the waves now. So now we move to the layer 2, which is the data link layer. The physical layer defines a medium to transmit our signal. The data link layer represents the protocol that enables data transfer between nodes on the same network segment. Now, let's put this in simpler terms. The data link layer will describe the agreement between the different systems on the same network. Don't forget that on the same network, as long as a device can connect to the internet, we can have our smartphone, a smartwatch, a computer, the smart TV in the same home network. So this data link layer will now describe the agreement between the different systems on that network segment on how to communicate. A network segment refers to a group of network devices using a shared medium or channel for information transfer. For example, you consider a company office with 10 computers connected to a network switch. That's a network segment, just similar to what I explained when you have your own network and you have different devices connected to the internet. Yeah. So examples of layer 2 include the Ethernet, that is 802.3, and Wi-Fi, which is 802.11. We are very curious. These are just like the standards 802. No, it's 11. You can see these are like standards that govern wireless connection. Yeah. So that's just it. So their address, okay, good. Their address is called a MAC address, where MAC stands for Media Access Control. By now, you should be familiar with these terms, but if not, you can still take your time. They are usually expressed in hexadecimal format with a colon separating each 2 bytes. The 3 leftmost bytes identify the vendor. So this is what we're talking about. This A4 colon C3 colon F0 colon 85 colon AC colon 2D. So these first 3 columns will identify the vendor, and this last 3 column is going to be the unique address of the network interface. We expect to see 2 MAC addresses in each frame in real network communication over Ethernet or Wi-Fi. One, which is the destination data link address. That's where we are sending it to, the data link address for that. Then the source link address, that is the MAC address of the source. Then the remaining bits will show the data being sent. Let's take a look at this. So this yellow ink, that's the destination, while this blue ink is the source. You can have it here, the source, CloudNet, destination Beijing SD8. So that's just what it means really. Layer 3 is the network layer. While the data link layer focuses on sending data between 2 nodes on the same network segment, the network layer is concerned with sending data between different networks. Now in the home, like just trying to send stuff between the home network and your work network really. So in more technical terms, the network layer handles logical addressing and routing, that is finding a path to transfer the network packets between the diverse networks. In the data link layer, we gave an example of one company office with 10 computers, where the data link layer is responsible for providing a connection between them. Now let's say that this company has multiple offices distributed across various cities, countries, or even continents. The network layer is responsible for connecting the different offices together. The network below shows that computers A and B are connected, although on different networks. You can also notice 2 paths connecting the 2 computers. Now the network layer will route the network packets through the path it deems better. Examples of network layer include the Internet Protocol, the Internet Control Message Protocol, and the Virtual Private Network Protocol, such as the IPsec and the SSL/TLS VPN. It's okay if these terms are still strange, you get familiar with them with time. Layer 4, which is the transport layer. The transport layer enables end-to-end communication between running applications on different hosts. Your web browser is connected to the TriAcme web server over the transport layer, which can support various functions like flow control, segmentation, and error correction. Examples of layer 4 are transmission control protocol and the user datagram protocol, UDP. Session layer, layer 5. The session layer is responsible for establishing, maintaining, and synchronizing communication between applications running on different hosts. Establishing a session means initiating communication between applications and negotiating the necessary parameters for the session. Data synchronization ensures that data is transmitted in the correct order and provides mechanisms for recovery in case of transmission failures. Examples of the session layer are network file system and the remote procedure call RPC. Move on to layer 6, which is the presentation layer. The presentation layer ensures that data is delivered in a form the application layer can understand. Layer 6 handles data encoding, compression, and encryption. An example of encoding is character encoding, such as the ASCII or the Unicode. Various standards are used at the presentation layer. Now we consider the scenario where we want to send an image via email. First, we'll use JPEG, GIF, or PNG to save our images. Furthermore, although hidden from the user by the email client, we use MIME, which is the multipurpose internet mail extensions, to attach the file to our email. Now, MIME will now encode a binary file using 7-bit ASCII characters. So there are a lot of things that goes on in the back end that we are not aware of as the user. The application layer. The application layer provides network services directly to end user applications. Your web browser would use the HTTP protocol to request a file, submit a form, or upload a file. The application layer is the top layer, and you might have encountered many of its protocols as you use different applications. Example of layer 7 protocols are the HTTP, FTP, DNS, POP3, SMTP, and IMAP. Don't worry if you are not familiar with all of them, as I've been saying. It takes time, but you're going to get it. In summary, reading about the ISO OSI model for the first time can be intimidating. However, it becomes easier as you progress in your study of networking protocols. To help with your studies, we have summarized the ISO OSI layers in the table below. We have the layer number, the layer name, the main function, the example of protocols and standards. Now we have our questions. Which layer is responsible for connecting one application to another? Connecting one application to another. What's the hint here? The answer format should be a single digit. For example, if the answer is layer 5, you should type 5. Connecting one application, that should be the transport layer, right? Oh, good. I think we have it here. End-to-end communication. Which layer is responsible for routing packets to the proper network? That should be layer 3. That's the network, right? Okay, good. In the OSI model, which layer is responsible for encoding the application data? Encoding the application data. We have layer 6 here. Data encoding, encryption, and compression. So layer 6 is our answer. Which layer is responsible for transferring data between hosts on the same segment? On the same segment, that should be layer 2, data link layer. Good. So that brings us to the end of the OSI model. The next thing we'll be looking at is the TCP/IP model. Now that we've covered the conceptual ISO OSI model, it's time to study an implemented model, which is the TCP/IP model. The TCP/IP stands for Transmission Control Protocol / Internet Protocol and was developed in the 1970s by the Department of Defense. Oh, Why Department of Defense? Why? One of the strengths of this model is that it allows the network to continue to function as part of it are out of service. For instance, due to a military attack. This capability is possible in part due to the design of the routing protocols that to adapt as the network topology changes. In our presentation of the ISO OSI model, we range from bottom to top from layer 1 to 7. In this task, let's look at things from a different perspective, that is from top to bottom. From top to bottom, we have the application layer, the transport layer, the internet layer, and the link layer. Now, what the TCP/IP model does is just like it kind of like compresses what we have for the OSI model. So for the application layer of the TCP/IP model, it comprises of the presentation, application, and the session layer of the OSI model. Now, so we have it summarized in this table here. Now, many modern networking textbooks will show the TCP/IP model as 5 layers instead of 4. So now it just lets you know that some textbooks will show you as 5 layers, some will show you as 4, whichever it is. Just know that we have the application layer, the transport layer, internet layer, link layer, and you may or may not have the physical layer represented. In the following tasks, we will cover the IP protocol from the internet layer and the UDP and TCP protocols from the transport layer. So what layer does HTTP belong in the TCP/IP model? That's going to be the application layer. How many layers of the OSI model does the application layer in the TCP/IP model have? What does it cover? It covers 3: application, presentation, and session. Now we're moving very fast. We're moving to the IP addresses and subnets. Should we do this now? Okay, fine, let's just cover it. When you hear the word IP address, you might think of an address like 192.168.0.1 or something less common, such as 172.16.159.243. In both cases, you are right. Both of these are IP addresses of IP version 4, and every host on the network needs a unique identifier for other hosts to communicate with him. If I were to speak to somebody now, like on the phone, I most likely would need their mobile phone number just to be able to communicate with them, right? So that's just like basically what it means. Without a unique identifier, the host cannot be found without ambiguity. When using the TCP/IP protocol suite, we need to assign an IP address for each device connected to the network. One analogy of an IP address is your own postal address. Your postal address allows you to receive letters and parcels from all over the world. Furthermore, it can identify your home without ambiguity, otherwise you cannot shop online. As you might already know, we have IPv4 and IPv6. IPv4 is still the most common, and whenever you come across a text mentioning IP without a version, we expect them to mean IPv4. So what makes an IP address? An IP address comprises of 4 octets, that is 32 bits. So being 8 bits, an octet allows us to represent a decimal number between 0 and 255. An IP address is shown in the image below. We have 192 octet 1, 168 octet 2, 1 octet 3, and 1 octet 4. Now, at the risk of oversimplifying things, the 0 and 255 are reserved for the network and broadcast addresses respectively. In other words, 192.168.1.0 is the network address, while 192.168.1.255 is the broadcast address for this segment here. So sending to the broadcast address targets all the hosts on the network, as name implies, broadcast. With simple maths, you can conclude that we cannot have more than 4 billion unique IPv4 addresses. If you are curious about the math, it is approximately 2 raised to the power 32 because we have 32 bits. This number is approximate because we didn't consider the network and the broadcast addresses. Now, looking up your network configuration, I think at this point, let me start my attack box so that it can start loading against the next task. Okay, right. You can look up your IP address on the MS Windows command line using the command ipconfig. On the Linux and Unix based system, you can issue the command ifconfig or IP address show, which can be typed as IPAS in the terminal window below. So if you go to your desktop area, you go to the search, type CMD, it's going to show you the command prompt. Then you can type ifconfig to show you ipconfig rather for the MS Windows to show you. I'm waiting for this machine to start and we can do something similar. The terminal output above indicates the following: the host IP address, which is this, the subnet mask, which is this, and the broadcast address, which is 192.168.255. Let's see, can't seem to find that. Okay, yeah, we have the broadcast here. So let's use IPAS to compare how the network card IP address is represented here. So for this one, we have the host IP. Oh no, what's this? We have the host IP. Okay, what's happening? We have the host IP and the broadcast address. So if you are wondering, a subnet mask of 255.255.255.0 can also be written as /24. The /24 means that the leftmost 24 bits within the IP address do not change across the network, that is the subnet. In other words, the leftmost 3 octets are the same across the whole subnet. Therefore, we can expect to find addresses that range from 192.168.66.1 to 192.168.66.254. You can see that it's just the last octet that changed. The first 3 octets didn't change because we have the subnet mask as this. Private addresses. As we are explaining IP address, it is useful to mention that for most practical purposes, there are 2 types of IP address: the public IP address and the private IP address. The RFC 1918 identifies the following 3 ranges of private IP addresses. If you are very curious, you can just type RFC. What's the code again? 1918. Yeah, okay, good. So we have the, and just go to the data tracker and we can read up the what the RFC means request for comments 1918. So we can just go through it, read it, and get a better understanding. Now we have 3 ranges of private IP addresses. This 10.0.0.0 to 10.255.255.255. We also have the 172.16.0.0 to 172.31.255.255. You can see the other way it can be written. We have 192.168.0.0 to 192.168.255.255. Subnetting is a whole big deal on its own. I mean, it actually take time to get familiar, but once you understand it, this thing becomes very easy. We presented earlier an analogy stating that a public IP address is like your home postal address. A private IP address is different. The original idea is that it cannot reach or be reached from the outside world. It is like an isolated city or a compound where all houses and apartments are numbered systematically and can easily exchange mail with each other, but not with the outside world. For a private IP address to access the internet, The router must have a public IP address and must support network address translation (NAT). At this stage, let's not worry about understanding how NAT works, as we revisit it later in this module. Now, before moving on, we recommend memorizing the private IP address ranges. Otherwise, you might see an IP address such as 10.1.33.7 or 172.31.33.7 and try to access it from a public IP address. What this means is that if you have a private address, it cannot be accessed from a public address, right? Routing. A router is like your local post office. You hand them the mail parcel and they would know how to deliver it. If we dig deeper, you might mail something to an address in another city or country. The post office will check the address and decide where to send it next. For example, if it is to leave the country, we expect one central office to handle all shipments abroad. In technical terms, a router forwards data packets to the proper network. Usually, a data packet passes through multiple routers before it reaches its final destination. The router functions at layer 3, inspecting the IP address and forwarding the packet to the best network so that the packet gets closer to its destination. What this means is that if you're on if a node, that is the host, is trying to access something, a resource, what the router does is just to find the shortest possible distance and make sure it gets to the right destination. It's going to do its own inspection and all that. Which of the following IP addresses is not a private IP address? Now we are going to